All right, we are live on the recording. Cool. Welcome to SQL Friday number 90. It's the last of the season, so it will be a summer break after this. Call for speakers for next season is open. So if you're on the call or if you listen later and you feel like doing a talk on SQL Friday, then go to sessionize.com/something that I will post in the chat because I forgot the URL. You don't have to be as experienced as Edward, who is our star today, to do a talk. It could be your first time, and if it is your first time to do a talk, then we can help you find a mentor if you want that. It's okay if you don't want it to. So as I state in the call for speakers notes, SQL Friday is for everyone, and that comes also for the speakers. So if we can make it a platform for a new speaker to start their speaking career, I'll be really happy about it. So please do submit a session for the next season. I have talked enough. Welcome, Edward. Or Ed, which one is it?
It can be Ed. Ed is nice. I like Ed. Let's go ahead and share some stuff here. And all right, can you see me? Oh, my stuff.
See it. I see the presentation. Yes.
Excellent. All right, then. We good to go?
We're good to go.
All right. Well, thank you very much for having me here today. I was chuckling earlier because it's noon there. It's 6 in the morning here, but I get up very early. So this is beautiful. I'm awake. I'm happy. I'm chipper. And 12 hours from now, I won't be. So be glad it's now and not later. This is a great topic. I love it. Columnstore indexes are a wonderful tool, and this is really a great intro, intermediate dive into them, how to use them, how to not use them, and what they're best for. I just really want to dive right into this and have a lot of fun with it. I have loads of demos, and let's just go ahead and do it. This is me. I've been speaking and writing and doing a lot of things in the SQL Server world for a long time. I enjoy this. I find it interesting. Presenting, being in these sessions, talking to people and learning from others as well. This is a wonderful experience. Feel free to contact me afterwards. I'll have my info at the end as well. Ask questions, give me comments, tell me I stink, whatever. It's all good. And yes, the SQL Saturday umbrella, one of my favorite giveaways ever. Mine broke last year and I was very sad. Anyway, here's what we're going to do. We're going to quickly review OLAP data. What is it? Where can we store it? What can we do with it? And establish Columnstore indexes is a great way to store it. Not always, but sometimes. And then really the rest of it's going to be all about how to best use them. And I'm going to sprinkle in loads and loads of live demos because we all know live demos are fun. They're great. They're risky. They can break, and we all love that. So we're going to talk about really everything there is, the basics about Columnstore indexes, and really how to make the most of them. I have more advanced material out there. If you're interested in more advanced material, the really nitty gritty of like, how do we store the Columnstore data on pages and compress it? That's later, not here. But for now, this is a good start. And an important note is everything in here uses SQL Server 2019 and 2022. Everything I'm talking about here is on newer versions. Columnstore indexes were introduced a long time ago. When they were first introduced, they were far more limited than they are now, and the use case was much smaller. So they've evolved from version to version, 2014, 16, and so on, 17, 19, 22. So if you're using an older version of SQL Server, just be sure to verify things before you do them and just, test before putting things out there. It's always good advice, right? Great. OLAP data, this is our analytic data. This is the big stuff. This is the data that we store about our data. You have your transactional databases where you store your orders and your customer info and your processes and things that are being updated, inserted, and deleted all day long. Then eventually you want to report in that data and do some analytics and some machine learning and understand it better. So you take all that data and you begin throwing it somewhere and summarizing it and doing things with it. And now you have millions and billions of rows of stuff that you want to make pretty charts off of or make decisions based on. Where do you put it? And there's many places to put it. And I'm not going to try to pretend that SQL Server is the only place for your analytic data. That would be a lie, and that would not be a nice thing to do. But you can put it in many places. If you have very unstructured data, if you have mountains and mountains of files and rows of data, and you don't want to go summarizing it and ETLing it and crunching it into beautiful little facts and dimensions, you're not sure what you want to do with it. A great place to put it would be an unstructured data source. A place like Hadoop would be perfect. Throw it all in there, figure out what it is you want with it, and if you eventually have a very strong use case for a specific structure, you can structure it into something more warehouse-like later. Great for unstructured data or where you just don't really know what you're doing and you want to play. A data warehouse is great for data where you really know what it is you want. Your business, you have a very good understanding of your business organizational needs. The place like analysis service is probably a little out of date now, but Redshift and many other tools out there exist that you can put your warehouse data in and use it. And have facts, have dimensions, have a cube maybe, however it is you want to structure it, you can, and then query off those facts and get information. You can use, there's many third-party analytics software solutions out there if you have less people working with you. If you don't have a database administrator who understands these things or an architect who understands these things, there could be great value in putting your data into a third-party piece of software, something like Snowflake, or even use Tableau or Power BI and park your data there and begin working off of it. There's many other places to put it out there. You can store your data in S3 and pull it out of there and then put it into your analytics software. There's many ways to do this. The biggest benefit of the third-party software is you don't have to really know everything and how it all gets stored. You don't have to know how to structure it and do it. You kind of just put your data in there and then use it. And of course, the downside of third-party software is getting it back out later. Maybe a problem if you decide I don't want to use this tool anymore. Getting your data out and then putting it somewhere else could be a giant hassle. The last two options are I want to keep my data in my transactional database server. What do? I want to keep it in SQL Server. And for the record, there are Columnstore solutions elsewhere. They do exist in MySQL and in Postgres and other solutions out there if you use those primarily, but this is a SQL Server presentation, therefore we're going to talk about Microsoft and SQL Server. When data is small, a lot of people throw it into transactional tables or OLTP tables and say, you know what, all of my order processing data is here. I'll just roll up some analytic data here as well. It's not that big and I can report off of it. And in general, when your data is small, that's fine. Eventually your data gets bigger and bigger and bigger, and just dropping it in some clustered index with some non-clustered indexes is not going to cut it anymore. When you have billions of rows, this gets kind of slow, and you can do it, but it'll be expensive, and it's not really optimal. And so the last possibility here we're going to look at, and there are other choices out there where to put your data, but this is what the whole presentation is going to be about, is store your analytic data in analytic tables in a relational database. Huge benefits of that are it's alongside your transactional data. It's near it. You can work with it and query it just like any other table you're used to doing. And it's pretty darn efficient. This brings us to Columnstore indexes. What's a Columnstore index? And this is that OLAP structure. Your data is still parked in SQL Server. It's in a database. It's written to pages, but this is a special structure that is made for larger data. And by the way, are we doing questions afterwards? Is that kind of the plan here? Questions afterwards or questions midway or no questions?
It's up to you. How do you want it?
Okay, I'd be cool with questions along the way. If you see any, I'm not going to see them, but if you see them along the way and want to just kind of pause me at a nice stopping point, I'd be happy to take a little break and answer a few questions. I think it's a little nicer than waiting to the end for the question that was asked 50 minutes ago.
Absolutely. So if anyone has anything, just normal routine, put it in the chat and I'll relay it to Ed.
Thank you. I may talk a little quickly. I get that once in a while, so feel free to slow me down and stop me at any point. I don't mind one bit. So Columnstore indexes are an amazing tool, and Microsoft will tell you they increase your workloads by 10 to 100 times the speed, and you'll say, ha, you're joking, but that actually really is true. And the real key to Columnstore indexes is that your data isn't stored in rows. So when you store your transactional data in a regular clustered index, you store your data column by column, row by row. So if you have a table with 20 columns, you'll say, all right, here's row 1, column 2, 3, 4, 5, 6, all the way to 20. Then you'll start your next row, and it's all just contiguous data. Obviously you can have page splits and things like that, but the idea is your data is basically stored continuously, row by row, column by column. What happens when you want to say get a sum of a column over 5 million rows? For a clustered index and no supporting indexes, you're stuck having to scan the whole thing, grab all the data and bring it all into memory just to get that one column. Maybe you have some non-clustered indexes that speed it up a little, but you're still stuck doing a lot of scanning because you need 5 million rows. And 5 million rows means getting 5 million rows of something out of some index. Columnstore index says, all right, we'll compress it by column. We'll flip it on the side, and now we can get what we need that way. we'll talk a lot about how that works and why it's fast. The technology underlying these things has been used before in many tools. It's mature. This is not some toy. This is pretty amazing stuff, and the compression is very impressive. Because it's natively stored in SQL Server, you can just query these tables like regular old tables, no special syntax. It isn't like full text where you need special predicates to make it work, or stop lists and things like that. You just put the index on. We'll talk about how to optimize it, and then you use it, and it's faster and it's better. A key, though, is despite the fact that I'm calling it a Columnstore index, it's not just another index. This is a pretty impressive way of storing data. There's a lot happening under the covers to make this awesome, and therefore it isn't just another index and shouldn't be viewed as just some non-cluster index that makes things a little better. This changes how your data is stored and makes it very, very fast for analytic data.
I have a question for you, Ed, or
Sure.
Manit has one. Is there any performance issues if one of the databases is having Columnstore index in all tables and you join it to another tables in another database which don't have Columnstore indexes?
Nope. The key really is filtering. You're so far ahead of me right now. It's amazing, but I do appreciate it. Really, filtering is what controls it. But if you join Columnstore to non-Columnstore, each table is queried independently, filtered, aggregated independently, and dealt with separately. So you're not going to break a Columnstore index by joining a non-cluster Columnstore index table. But interesting question.
Yep.
So why are these things fast is a great question. You're going to ask me, why is it so much faster? How can it be 100 times faster? Give me a break, Ed. You're full of it. And I'm not completely, at least this time. Compression is really the huge key here. Because data is stored column by column instead of row by row, you can compress it way better because the data in one column will have very similar values. Imagine some status column that has 5 values and they're tiny ints. Well, it's only going to have the values 1 to 5, and they're probably going to repeat a lot. So it's going to compress wonderfully. A bit column is going to compress into next to nothing. Even text, things repeat a lot when you have analytic data. If you have 10 million rows of analytic data, most of it's going to repeat a lot. And when you do it by column, you have the same data type, and therefore it's going to see really awesome compression ratios. You can see 10 to 1, 21, even 30 or 40 to 1 very easily. And an important key to this compression is that, like regular indexes you're used to using, that data stays, if you have page compression or row compression, it's the same thing. Data stays compressed in storage, wherever that happens to be. When it gets read into memory, it remains compressed. And it's not decompressed till you need it for a query. Therefore, you save storage, you save memory. And that's a huge deal. So your buffer pool has more space in it, and your storage has more space in it, and therefore reading it is faster because it's smaller. I have whole sessions and presentations on just how the compression works. It's pretty cool. We're not going to do that here, though. We're not going to be breaking up our brains here today. So let's go over to demos. I haven't done any demos yet, and so that's silly. I've built all these tables already. They have a lot of rows in them. You don't want to sit here and watch while I build a table with 20 million rows, and neither do I. So I've created a table. I took fact order in the worldwide importer's data warehouse database. I put piles of data into it, and we can see how big it is just so we understand how big it is. So it's 23.1 million rows, not giant, but not tiny. And the data spans about 4-ish years. Cool. And this is uncompressed, just, regular old non-clustered index, clustered index table. Now I create a page compressed table. Same exact thing, but I page compress it. See, compression page. And I put a non-clustered on it. And then I can create a table with a Columnstore index on it. Same idea, just fact order big CCI. My naming isn't very creative. I didn't give it a cool name. Create a Columnstore index on it, and I can check again and say, all right. And notice all I did to create a Columnstore index was create clustered Columnstore index. Nothing fancy here. I don't have to go dancing through hoops of funny syntax. You just create it, and it's there. Same number of rows. I'm going to compare my table size. You don't have to really worry how this query works. I'll share all this for later if you feel like stealing some of my code. I don't mind. But I'm basically going to just go through some of these tables and see how big they are for the ones that I've created thus far. And you can see that the one with no compression takes about 5 gigs. The one that's page compressed takes about 2 gigs. The one with the Columnstore index takes about 340 megs. That's a big difference. Now, you may not always get that level of compression, but with data that repeats a lot, this is very common. So huge, huge compression here. About, what is this? Something like a 15th of the original size. So that's a big deal. The compression is a huge deal. It makes a big difference, and it's one of the primary reasons why Columnstore indexes are fast and efficient. But that isn't the only reason. There's like 10 more reasons, and I'll try to get it all in here today, and I'll talk fast if need be. Not a problem. Metadata is a big deal. We're used to metadata being very lightly descriptive, like here's the name of your column, here's the name of your table, here's the name of a view, or it's statistics. Statistics in SQL Server are estimates. You update them and they get better, but they're always estimates because you can't update them constantly. So they're estimates. The metadata stored in a Columnstore index is not an estimate, it's not a guess, it's accurate. So in line with the Columnstore index stored in dynamic management views that I'll introduce momentarily is metadata, and that metadata tells us exactly what's in every single compressed piece of data in the Columnstore index. Min, max, count, is it nullable, how many rows, how big is it? It's really huge, and that metadata can be used by the query optimizer to make your queries faster. That's a huge deal, and I'm going to introduce some additional topics later that rely on this metadata to function. So hugely important, and it's one of the new, and this metadata was done really well by Microsoft. When you look at it, it's really easy to read, really easy to use, and it makes your queries faster. So the optimizer will use this information to say, oh, this column can't have nulls, therefore I can join it like this instead and do a bunch of transformations and make your query faster. We'll go through the dynamic management views shortly, and you can see exactly what's inside of them and why it's pretty cool. Another piece of kind of a cool feature in SQL Server is batch execution. It was added to SQL Server for the purposes of Columnstore indexes, but in more recent versions, it's become available for other data as well, just transactional data, your normal indexes, and that's batch execution. Batch execution allows SQL Server to process data under the covers when you're executing a query, operator by operator, in chunks rather than one at a time. This is invisible to you, aside from if you go peeking at the execution plan. This is kind of invisible to you, but traditionally, before this existed, your rows would go speeding through the query from operator to operator until it came out and you were done one by one. It sounds slow. It wasn't really, but under the covers, for most transactional queries, it made sense. Updating 5 rows, selecting 1 row, looking at a few orders. It made perfect sense to process them one at a time. But in this world, we're processing millions of rows at a time, billions of rows at a time, and therefore doing 1 row at a time stinks. So under the covers, SQL Server will process them many at a time. And you don't see it, you don't have to do anything, it just works. That's the beautiful piece of it. But it makes your queries faster because it can shuttle hundreds of rows at a time rather than one at a time. And it's very easy to verify in the execution plan by taking a peek. Very simple example demo here. I'm going to make sure my execution plan is on. I'll run a really simple query, and notice how fast this ran, by the way. This is just a count, min, max, where the date is greater than a certain date off my Columnstore index. I get back my row count, my min, my max. That's what I wanted. If I go to my execution plan, I will see here the Columnstore index scan. And by the way, this is important. We're kind of trained in the transactional world to believe that an index scan is bad. For now, at least through SQL Server 2022, Columnstore index scan is the only operator you will see typically scanning a Columnstore index. It does not mean you scanned the whole thing. It just means that you used it. So don't be frightened by the word scan. It's normal. It's not a bad thing. It doesn't mean that I went through every single row. Very important. But you'll see in the execution plan here, 3 and 4 rows down, the actual execution mode and the estimated execution mode is batch. That's how you verify that you are in batch mode and rows are being chunked through in batches and not one at a time. Just trust me. If you want, you can play with this. I won't demo it here. You can turn off batch execution. You can force it off. You can run the same query. It will take longer, take more I/O. Cool. It's a very simple thing, but it's very effective, and it's very easy to check if it's working or not. On the right side of the house, writing data in large quantities can be slow. And so SQL Server built in bulk loading. This is important. You can, when you insert enough rows at once into a Columnstore index, 102,400, take advantage of bulk loading. Most of us are familiar, if we're familiar with bulk loading at all, it's through things like BCP or bulk insert, where you have a bulk logged mode, or you use BCP to get data out of a file and it bulk loads it really fast, and it's cool. But most other places in our world don't take advantage of that, but this does. So what happens is when you begin inserting a large number of rows into a Columnstore index, SQL Server says, hey, this is a bulk load. You're inserting a mountain of rows into a Columnstore index. It's probably a data load process because this is analytic data, which means that if it failed, you're probably just going to redo it anyway. Who cares? And so therefore, we'll do a bulk insert. And what this means is that you will insert your data in a giant batch, and it will not log the details of every row that were inserted. It'll log some general metadata about what was inserted and the start and the end, so you can roll back your transaction, but the details, the guts of it, are not there. And that's fine. It makes perfect sense. You want this. This makes your inserts faster. This also means that you can insert lots of rows at once. You can insert 1 million rows in one batch in a Columnstore index, and it'll be fast. And that's what you want. You don't want to go batching. Batching is kind of what we do in the transactional world to avoid blocking and deadlocking and stuff like that. But in this world, it's faster. An important note is that an update may be equal to a delete plus an insert, and it really is in this world, but you can't bulk insert an update. We'll talk about updates more later, but if you're just inserting data, this is very fast, and it's a really good feature, and it makes your transaction log bloat less. It makes your inserts faster. It makes your log growth less. It makes your backup, your transaction log backups smaller. Helps you all throughout the process. So don't be afraid of big batches. Bulk loading is awesome, and it will apply to Columnstore indexes whenever it can, which is almost all of the time. It won't work in an update or on row counts less than 102,400. So now that I've kind of introed why Columnstore indexes are cool, why they're so fast, I'll talk a little bit about the architecture of how they work, because it's very important to really understand how they work and to optimize and make the best use of them. You want to know how they work. There are some people out there, especially on the internet, because it's very easy to go on the internet and get information, that will say, oh, just slap a Columnstore index onto your data or your table and it'll be fast. And you're done. Your work is done. And that's not really true. It's sort of kind of sometimes true, but probably not. If you follow that advice, you may be happy at first, but you'll be sad later. And I don't want you to be sad later. So the way a Columnstore index is structured is your data is broken up into row groups. So you have, let's say, 1 billion rows of data, and it gets broken up and chunked into million row, about 1 million, 2 to the 20th, approximately 1 million rows per row group. So that's how you organize your rows into row groups. So if you had 1 billion rows, that's about 1,000 row groups. If you had 10 million rows, it's about 10 row groups, approximately. Each row group then, within it, has each column separately compressed into what's called a segment. So this little demo table here, displayed here, has 4 row groups, and it has 6 columns. Therefore, there's a total of 24 segments. Your segments will always be equal to the number of row groups times the number of columns. Each segment is the compressed data for one column for the rows within that one row group, separately compressed. So here within this Columnstore index example, there's 24 separately compressed structures within the Columnstore index. Here's where the metadata comes in. We can view the metadata and all of this, and it's very good. Again, feel free to steal all this code later. You don't have to go typing really fast. Just steal it from me later. I'll provide it afterwards. You can take it and have fun with it. So there's a bunch of dynamic management views. I won't go into extreme detail on how they work here, but the queries are here. You can kind of get what they are. sys.columnstore row groups provides information on row groups. Then I have a bunch of other tables, views and tables that kind of just join together to give some additional information. If I go ahead and run this query, you can see that here's all of my row groups for the index I created earlier. Had about 23 million rows, and I see 25 row groups. Starts at 0. Don't be fooled, starts at 0. And I go up here, and if you skip along the way, I've created this already, it's been used. I have one open row group that hasn't been committed yet. Great. I can see all my row groups, how many there are, what index they belong to, their state, the number of rows, how big they are. This is useful information. This tells me kind of how big my Columnstore index is, and I don't have to look at a jillion rows of stuff. It's just one per row group. So very useful information. There's more in there. We'll dig into that a little more later. The segments are those nicely compressed column bits within each row group. Again, it's sys.columnstore segments. Microsoft did a beautiful job naming these views. They're very easy to use. I query it and I get a row back per segment, and I can see, all right, I have a little more here. I have one segment per column per row group, which comes up with a total of 456 segments. I can scroll through here and see, all right, I see what column they're for, like customer key. I can see the row count. Does it have nulls for that column? Some information about the dictionaries, dictionary compressions, type of compression. Don't have time to talk about it here, but I did do a lightning talk on it earlier this season, and you can dictionary compress data. That information is here. You can also see the min and max ID for that value. If it's a number that fits here, it'll show you the number. Otherwise, it'll give you a dictionary lookup of some sort. And then the size of that segment is there too. So you can actually see how well each segment compresses, how well a certain column compresses versus other columns in your Columnstore index. So again, lots of metadata here. You can use it or not use it, but it's here, it's available, and it's pretty cool. And the optimizer uses this as well, which is kind of cool. It's there, it's available for the optimizer to use and make your queries faster. That's what our metadata looks like. It's very, very useful. It's cool that it's there, and the views are relatively simple and straightforward. All right. What do we do now? Oh, go ahead. Go ahead.
I interrupt you with a couple of questions. First one is from Gab, or maybe you will touch on it later. I don't know. Columnstore indexes on in-memory tables. Is that a go or a no-go?
I would say probably a no-go, and I will talk about it later. I don't want to go into too much detail now. I will just start by saying probably a no-go, but I won't say no.
So next question from Gabrielle. I answered shortly in the chat, but let's see what you say. Is it possible to apply these principles to a SQL Server 2017 to 19 standard edition on a table with 300 million rows with frequent inserts?
Yes. Yes, I know bulk inserts. I said there are 102,400 rows, and that's how they work. You can insert less rows, and I'll describe the process used for that shortly. It's not perfect, but it's good. If your table is insert heavy, and this is actually important. So for a Columnstore index, you want a table that's insert heavy and has no updates. Really, I mean it, no updates and minimal deletes. You can delete data, especially if it's the tail end of the table. You're getting rid of the old data, chopping it out. That's fine. But in general, you want a table with lots of inserts, no updates, and if there's deletes, they're ordered. You're hitting the end of your beta and it's going away. That's the ideal for the right use case. I'll talk a little bit more about updates and inserts and how they work shortly. But I appreciate all these forward-looking questions, though. I do like that. You're interested, and I love it. Thank you. So here's how we use our metadata to make Columnstore indexes faster. You've seen that we have row groups and we have segments. Each segment has a column, each row group has a section of rows with metadata describing everything inside of each row group and each column. So we know within each row group what the min and max values are for every column. And that's massively valuable. We also know which columns we need and don't need, and they're all compressed separately. So segment elimination is the first optimization the optimizer gives us, and it's awesome. There's the classic advice, only query the columns you need, and that applies here as well. Let's say I have my 6-column table, and I query just for A and B and nothing else. The optimizer can go and grab columns A and B and ignore the rest. It won't need to load columns C through F in memory like it would for a regular clustered index or a non-clustered index potentially. There's lots of columns in it. So therefore, if I have this 6-column table, I can ignore 2/3 of it automatically. So a general piece of advice in Columnstore world is only query for the columns you need for your query. And very often you're going to have some table with 40 columns, and you're just going to want to get a sum or a count of like 3 or 4 columns with a where clause and call it a day. That's very often what an analytic query looks like, and that's where this helps you out a lot. You'll just use the columns you need for your aggregate stuff, and the rest go away. You don't need them right now. So if you're only querying for columns A and B, those are loaded in memory and the rest are ignored, and things are faster. That's kind of the horizontal slicing of our data. What about the vertical slicing? Since the optimizer knows via the metadata the min and max values in every segment and every row group, what if we query some data that's ordered here by date? I throw new data in every day by date, and it goes back a bunch of years, and it goes forward a bunch of years. What happens if I query for just a small date range, and that date range is totally encapsulated in row group 1? If I do that, SQL Server can say, I know the min and max value for that date range. I know that date range is only in row group 1. It's not in 2, 3, or 4. Therefore, I can just skip 2, 3, and 4. This requires ordered data. I'll talk about that shortly. But if your data is ordered by a certain column and you query by that column, you will ignore all the row groups that don't have data you need. And that's huge. It means that I can ignore, in this case, 3/4 of my Columnstore index and return data for row group 1. The next logical conclusion from this is, what if I combine them? What if I combine segment and row group elimination together? I get even better optimization. So now let's say I query for a small date range, all in row group 1, and I query for just columns A and B. I do that, and I only need 2 segments. I have 24 segments in this index here, and I only need 2. I read 2 segments in memory, and I'm done. That's a big optimization. And the larger your table gets, the more this optimization becomes valuable. If you have data in a Columnstore index that goes back 10 years, you just want some numbers for last quarter. That's only 3 months of data. You're only looking for 1/40th of the data and maybe less columns. And so this optimization can slice away millions, billions of rows, gigabytes, terabytes of data. So it's huge, absolutely huge. Some more architecture that's worth talking about. How do you insert data that's less than 102,400 rows? If you can't bulk insert it, what do? What if you update rows? And the answer is use the Delta Store. The Delta Store was added to SQL Server to Columnstore indexes to help deal with the fact that people do trickle load data sometimes, and we should be able to do that. How does it work? The answer is you have the Delta Store, and there could be multiple of these on your Columnstore index. And basically, each row group within here is basically a B tree. It's a classic clustered index that stores your data. It's not ordered in any particular way. But when you insert 1, 2, 10, 50, 100 rows in your Columnstore index, it gets plopped into basically a heapish kind of structure. It's not really a heap. It is structured, but it's kind of like a heap. And it sits there. And then asynchronously in the background, a process called the tuple mover will occasionally come through and push those rows into your index whenever it feels is best. It does it all in the background. You don't have to worry about it. If you read your table, it will check the Delta Store first to see what's in there. Is that data needed or not? And then it'll check the Columnstore index. If you're writing data, it'll check that Delta Store as well and do whatever it has to do in there in addition to the Columnstore index. If you don't have any rows that have been inserted in tiny batches, haven't updated any rows, there won't be Delta Stores. They only exist when needed, and then they're not there when you don't need them. You may ask yourself, all right, well, that stinks. A heap? I don't want that. That's slow. But the answer is it actually isn't that slow. The reality is that the Columnstore index is compressed using some pretty amazing compression algorithms, and they're expensive. And adding rows to it means decompressing it, adding your rows, recomputing all that metadata, and then recompressing it. And that can be kind of slow, especially if you're updating a lot of data. It can get slow. And that was the reason why when Columnstore indexes were first released, they were read-only structures because this hadn't been done yet, and the writing was too expensive. So the Delta Store sounds inefficient. It's actually very useful because it makes it so that if you insert 100 rows, you don't have to stop the presses and do a bunch of work in your Columnstore index. You just throw it in the Delta Store, then in the background it'll get dealt with later. And that's very important if you're updating, let's say we're inserting rows into 100 different row groups. Having to decompress and recompress all of them would be very expensive. So this is an optimization. It's a good thing. It works completely in the background. You do nothing, and it works. You can kind of influence it with reorg processes, with maintenance, but you don't have to. So just trust the Delta Store is a good thing. You like it. You want it. Don't complain about it. It's not going to slow things down. It's not a reason to not use a Columnstore index. If you trickle insert data, it's not a big deal. I will say, though, inserting in larger batches is better. And if you're collecting trickle data, there could be a benefit in throwing it off into a sidecar table first and then bulk inserting it later. That could make things faster. So how do insert operations work then? We already know that 102,400 rows or more will get bulk inserted. Very, very fast, very, very speedy, minimally logged. Less rows get inserted into the Delta Store. And then any batch up to 102,400 goes in the Delta Store and gets processed later. So I kind of mentioned it already, but you want to insert larger batches. In fact, you can batch your rows in 2 to the 20th rows. And when you do that, you'll create a brand new row group, throw data into the new row group, and it'll be kind of your own nice, fresh row group all created just for your data. You can do larger insert operations if you want. It isn't bad, but you still have to do log it all. So I wouldn't recommend inserting a billion rows at once. It will be slow. You still have to process it. That is expensive. But I encourage you to insert larger batches, up to maybe a millionish rows. That's a nice batch size in a Columnstore index, but less is fine if you have to. I would never say don't use a Columnstore if you need to insert smaller row counts. Whoa, my phone fell. That tells me the time. Cool. This is recorded, right? Great. I love those little bloopers. Next, how do we delete data in a Columnstore index? That's a good question as well. And the answer is very similar to with inserting, is that we don't actually delete the data. If you delete 1 or 5 or 10 or 100 rows, SQL Server will not stop the presses, decompress all the row groups, delete some rows, recompress them all, and then let you go, because it's going to be slow. It's going to take a long time, and if people are doing analytics, it's going to stop them, which stinks. So like the delta store, there's an additional structure called the delete bitmap. The delete bitmap there can be multiple of these, and it overlays your row groups. And it's really just a bitmap with ones and zeros that says, hey, wherever there's a 1, that row is deleted. If it's a 0, it's not deleted. If there are no deleted rows, there's no delete bitmap for those row groups. Done. And again, the reason for this is we've got to keep track of our row groups, but we can't change them constantly. So therefore, this kind of fixes that. And when you run a query that hits deleted data, it's going to check the delete bitmap first, and that'll tell you which rows are deleted. It'll then go in and read the row group, ignore those rows, and then continue. So how does this look like in our metadata? I can go in right now and take a look. I may already have deleted rows here, and if I do, hey, I already have some. So I've already done some work for us. You can delete some rows, and when you do so, they'll appear as deleted rows in your metadata. So you can go in and look in your row group data and see, hey, I actually have a Columnstore delete bitmap there with some rows in it. This tells me that rows have already been deleted. So this delete operation here, I've already done it. Do it again, I suppose. I'm not sure if there's anything there right now or not. Is there? Nah, I deleted nothing. Doesn't do anything. But I can see how many deleted rows there are and how many there are in total. Again, the metadata is very, very useful. It tells us really everything there is to know about our index. And so we can know is there a delete bitmap or not. And again, like before, deletes aren't bad. Do not avoid using a Columnstore index because you delete data. That may not be the right choice. Do know, though, that they're soft deleted. So data is not really deleted from a Columnstore index. It gets soft deleted. And because of that, the soft delete means that it's still going to be there. It's still going to consume space. But on the bright side, in newer versions of SQL Server in 2019 and 2022, background processes will clean them up over time, and you can do reorgs to clean them up as well. It used to be they sat around until you did a rebuild. That isn't true anymore. And so maintenance is getting better. You can clean that up. We'll talk about that a little bit more later. Last but not least, updates. I've already said don't update data in a Columnstore index, and I mean it. An update is literally a delete followed by an insert. So you will write data in one transaction to delete bitmaps. You'll then also insert data into the delta store, and you cannot bulk insert from an update. Doesn't work, can't do it. SQL Server can't handle it. Therefore, you got to do writes to two different heapy structures, and the delete bitmap is kind of like a heap. You got to write to two heaps. You got to do it all in one transaction, and the more row groups you hit, the more abysmally slow this gets. In fact, it'll get exponentially slower. Can't bulk load, can't benefit from any optimizations at all, and as a bonus, it will cause fragmentation. You'll have deleted rows sitting around, and you'll have inserts of data that could be over here in your ordered data over here. I'm going to talk about ordering your data soon. It's very important. The real theme here is don't update in a Columnstore index ever. If you need to update, do a delete followed by an insert. It sounds silly. Just trust me. The process of doing all this in a transaction and doing all that work in one quick bout is expensive. And at a very large index with a lot of rows being updated and a lot of row groups, you'll find there's some serious pain to be experienced on your SQL Server. So, therefore, avoid updates. This data has already been updated, which means you can see it already. I update 5 rows. I go back in and look at what we saw kind of before, and you can see now, I deleted 100, and now I updated 5. And I can see that I have 5 in the delta store, meaning I've inserted 5 new rows. It got trickled inserted into the delta store heap, and it got split across 2 row groups. Then I also have 5 in the delete bitmap because an update is a delete plus an insert. It occurred pretty fast here because it's a smaller Columnstore index, and I wasn't touching a lot of data. The bigger it gets, the exponentially worse it gets. But you can see the effects of updates in your data pretty easily using metadata. Now I'm going to run through the best practices, and these really are best practices. You don't have to always do things perfectly, but the more you follow these tips, the better off you'll be. This is probably the most important one that isn't very well documented, and it is documented by Microsoft, but it isn't in your face obvious, and that is when you make a clustered index, a regular old row store clustered index, or a non-clustered index, they're all ordered by your key columns. You have key columns, and you say, hey, I want to do a clustered index in this special ID. I want to do a non-clustered in this date. Your data is ordered by those columns. In a clustered index, it's not ordered. In a clustered column store, it's in all the columns automatically. You don't pick the columns. It goes in every column in the table. In a non-clustered column store, you pick the columns, but there's no ordering done. The order is whatever your order of your data is under the covers already, and that's it. So if you don't order it, it's unordered. You can't benefit from row group elimination. When SQL Server says, hey, I want 1 month of data, let me find all the places where that 1 month exists. If your data is not sorted by date, it can't benefit from it. So the key here is that order is not defined in a column store index. It's ordered by however you insert it, whether it's in order or not. Row group elimination, again, it's really important to making your column store index fast. If you can't benefit from row group elimination, your queries won't be fast. They won't be. Your deletes will be slower, your inserts will be slower, everything will be slower because you've got to deal with the fact that your data is scattered everywhere. Typically in the analytic world, time is your dimension used for ordering because you're going to be doing quarterly reports, annual reports, monthly analytics. You're going to do some year over year, month over month, day over day. All of that's based on time. You may have a different dimension you order by, and if so, that's cool. You may want to order it by that or do a non-clustered, that's cool. But typically time is what you're going to use. If you order your data by time, you need to actually enforce that order or it won't work. But naturally, data kind of tends to order nicely by time because you'll say, hey, I built a brand new analytic table. Here's our first date of data. Done. Here's the next date. I insert it tomorrow. Day after, day after, day after. Your data gets inserted in order. It's perfectly ordered. Data order will not only allow row group elimination to occur, making your queries faster, it will actually save storage because typically data that is close to itself in proximity by time will be more similar. And if it's more similar, it compresses better. And in some data sets, the one I'm going to show you here, it's really dramatic, the amount of savings you get. So here is my column store index without order. I'm looking at my order date key column, which I will probably be querying by a lot to run my queries to see, hey, quarterly, monthly, daily, whatever. And you can note here that min data ID stored in the segment metadata and the max data ID are the same. This tells me that my data is not ordered at all and that the minimum value and maximum value for the order date is the same in every segment. Which means that if I need to go look for a certain date, I've got to search all my segments. If I have 1 million segments or 10 million segments, it's going to be pretty slow. No question about it. Now, there is some useful information added in here we can look at. If I go to my statistics IO, I up here at the top, way back in the beginning, turned on statistics IO. That'll give me some IO information about what we're doing here. Oh, now I've done it. Shouldn't have done that, huh? I want to look for 1 month of data, just 1 month of data. My stats IO tells me, hey, I read 24 segments and skipped 0. The skipped 0 means there was no row group elimination. It had to go through every single row group to get what it needed, and that does cost reads. A lot of your column store reads will not show up as regular row logical reads. The logical reads will probably be your metadata. Your data is stored kind of as lobs, and so you're going to have I have 12,500 reads here to get 1 month of data. That doesn't sound very efficient. I mean, it was fast. Data's nicely compressed, but not exactly what I expect out of this amazing structure I just sold to you. I'm not a scam artist, I promise. We'll do better. So I'm making a brand new table here. Same table as earlier. I'm creating a clustered index. Again, note, no column list here. Sorry, I'm creating a regular clustered index ordered on order date key. This is important. Before I create the clustered column store, I'm going to create a regular clustered index. Sorry about that. And this is important. I'm going to order my data by order date key. I'm going to force my order on it. I'm going to insert my data. And now what's happened now at this point is I have a table where the data is ordered by date, perfectly ordered. I can use row group elimination on it once I have a column store index. So I create the column store index. I do max stop 1 because I do not want parallelism. I do not want my data to be threaded into it in multiple streams. I want 1. I want it to be in order. And I've drop existing on. So now I have an ordered, clustered column store index on a table that had previously been ordered by clustered index. I run my simple analytic query here to get a sum, get back my results. First off, I notice I read 2 segments and skipped 21. More segments you're skipping, the more you're taking advantage of row group elimination. This means that I've skipped 2/23 of the data that I looked at here and inspected. I can also note that my logical reads, my reads needed to get that data were way down from, what was it, 15,000 down to like 195. That's pretty good. So ordered data is much, much faster, and I can verify the order in the metadata. If I go in and look at my order date key column, I can see here that my min and max data IDs progress. They go higher and higher. If I needed to get data for a very specific ID in here, a specific date, note these are just numbers that represent dates. That's all they are. They're lookups because you can't store any data type you want in here. It's got to be a numeric. I can just look at it, and at most I'll have to go to 1 or 2 segments to get one date, and I'm done. 1 or 2 row groups, and I'm done. So this is great. I can see row group elimination work. I can see the ordering in my data, and now if I insert new data into my Columnstore index after the fact, and I keep putting today, tomorrow, the next day in, it'll remain ordered, and this order will get maintained going forward because it's already ordered by date, and the new data coming in is ordered by date. Cool. Pause to see if anything happens.
Another question.
All right, that's what I was looking for.
When you do the insert into the Columnstore, should you use max.1 on the insert as well?
Nope, you do not have to. The max.1 was used here exclusively because I'm building an index, and if it takes advantage of parallelism, it'll build it in multiple threads and break the rows out. And the end result will be that if I break it into like 4 groups of rows and then bring them back together at the end, it won't be in order. It'll be kind of like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, instead of 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. This is only for building a clustered column store that's already being pre-built on already existing ordered data. It's kind of a use case you may or may not ever need. If you're building a brand new clustered column store, you won't need it. Of course, in a non-clustered column store, the order is prescribed by your underlying row store indexes. So if you have a cluster index and you slap a non-clustered column store on top, that clustered row store will define your order. You can't specify order there. It's the order of your clustered regular old clustered index, and that's that. But here you can impact your order because your column store has no built-in order. So either you provide order or there's no order.
Another question from Milos. What's your experience with rebuilding of large column store indexes online? If a column store index is heavily fragmented, we need to rebuild it. But the question is the table really available during the online rebuild?
Yes, it is, as long as it's online. I would recommend investigating reorgs. A column store reorg does a lot of the work for you. It will not recombine and fix all your undersized row groups for you, so it isn't perfect. But a reorg can do a lot for you. If you have to do an online rebuild, do it. My next advice coming up shortly will help you, though, and that's to partition your data. Rebuilding 100 million rows or 500 million rows is painful, but doable. Rebuilding 1 billion rows is painful. So partitioning your data a little bit can help. But the online is truly online, and you can take advantage of it if you want.
Cool.
All right, jumping back. That was data order. Very, very important. Partitioning is a great thing to do. If your data is massive, if you have billions and billions of rows in your table, there's a benefit to partitioning. It really is made for it. A large column store is just built for this. The perfect mix of features. You know, your row group elimination is slicing your data up by row group, and partitioning simply slices it more. There's a couple benefits here you get. First off, if you're ordering your data by date and you partition by date, everything's beautiful. Everything matches up nicely. You can actually benefit from partition elimination. It'll help you here. If you partition your data based on date and you run a query on date and 3 partitions are not needed, they'll get ignored. You don't usually partition for performance, but this will improve performance further. The other benefits of partitioning are maintenance. You can now back up, rebuild, reorg. All those things can be done on a partition by partition basis. Very often in the analytic world, you have your new data that's being written to constantly, and you have your old data that barely gets touched. And when that's the case, you don't have to rebuild the whole thing. You don't have to reorg the whole thing. You can just rebuild and reorg your new stuff and call it a day. That can save you trouble. You can also partition swap or partition truncate and do other snifty, snazzy, cool things that are like magic. And again, if you partition, you can do that. If you don't, you're kind of falling back on T-SQL to solve your problems. When you're talking about many, many billions of rows of data or very large data sets, that can be painful. An important note on this is that when you build a column store index in a partition table, Each partition basically contains what can be viewed as its own column store index, its own structure. Each one has its own set of row groups and segments, which means don't make your partitions too small. You want a partition to have hundreds of millions of rows or more. A partition with 500,000 rows will be suboptimal because you want a bigger row group. You want a filled up row group with 1,000,000 rows, 2 to the 20th rows. 500,000 rows can't do that. So partitioning is a wonderful, wonderful feature. To demo it, I will go ahead and create a partition setup here with file groups and files and a function over years and a partition scheme on that function. I'll create a table on top of that partition. Really, everything's the same here, by the way, up until now. I'll put a clustered index, do the whole ordering thing because I want my data ordered. I don't want unordered data. I'll do my max stop one drop existing trick to swap the indexes. And so now I have a ordered partitioned column store index partitioned by year, and I have 4-ish years of data. If I run my same analytic query from earlier, getting a sum for 1 month of quantity, I get my result back, same as before. I can see here I read 1 segment and I skipped 2. And my reads are even lower. What this tells you is that all the rest of my column store index for 2015, 2014, 2013, whatever, 2017, ignored, completely ignored. All I have to do is consider the 2016 data and nothing else. That's huge. Huge, huge optimization. And then it also allows for all of your maintenance and cool trickery later on if you want to partition swap or get rid of your old data or move it somewhere else or compress it differently. Avoid updates. This is a best practice. I mentioned it earlier. I'll simply mention it again. If you've got to do it, replace it with delete and insert. But in general, updates are a hazard. They can slow down your column store index writes heavily and even cause resource problems in your server. If you do a giant update on a giant column store index across many, many row groups, you could actually cause serious contention issues, memory issues. They could take a long time. Don't do it. You could break tempdb or the log. It's generally something you want to avoid it. If you want to monitor it and do it manually on a few rows, you're welcome to. But any automated processes and data loads, definitely avoid updates. It's a huge hazard too when you're migrating code from row store to column store. Make sure that whatever processes you have that load data get combined together, get reviewed, and just make sure to avoid updates. If you can, maybe do the updates in a staging table first. Drop your data into a temp table, then do all your mucking around with it there, and then insert your final data set in one nice bulk insert to your column store. Much, much faster, less issues. Trust me, you'll thank me later. You just will. We talked about it earlier, query fewer columns because segment elimination means that every column you don't query for is a column of segments you don't have to read in memory. So simply query fewer columns, only the ones you need, and it will be faster. If you have 100 row groups, every column you skip will be all those row groups skipped for the query you need to get. It's fast, it's simple, it's classic advice. It doesn't change here in the column store world. How about archive compression? We can compress our data more. We don't have to stop here. We can compress it more. Archive compression is a even tidier, more compact compression algorithm. It does more to your data to compress it, meaning it's more expensive to compress and decompress, but it's great for cold data. It's great for warm data. It's great for the old data you don't touch very often, and it will give you an additional 10 or 20% at least, but it will slow your queries down a little bit, and it'll cost more to execute them. And as a bonus, you can do it on a partition by partition basis. So if you got 10 partitions and a couple are the old data, you can archive compress the old data, and then the new data can be standard column store compression. I'll create another table like before. This is my archive compressed table. Everything is the same. I'm going to insert my data. I'm going to order it. I'm going to do all the same things I did before. And then the only difference is going to be data compression equals column store archive. Everything else is the same. I didn't change anything else. Let's compare our table sizes now of these indexes and see how they look. Wait for it. Wait for it. Wait for it. Oh, I have my, I did it to myself. I apologize. I have my execution plan on. That's not a pretty execution plan. Let's do that again. Much better. So you can see all the index sizes for all of the columns or indexes we built today. We can see the We have a covering index on one is about 5 gigs, a page regular index is 5 gigs, page compress is 2 gigs, partitioned, just partitioning the data and ordering it. So we ordered it, it went down to 113 gigs. Now ordered partitions got a little bigger. Partitioning the data, I had to slice up my row groups a bit. And so I made it actually a little bigger. That isn't bad. Partitioning has so many valuable uses that it's still worth doing potentially. But we can see here how things get smaller and smaller and smaller. My regular column store is 341 megs. If I archive compress it, it goes down to 217. Pretty big gain. If I order it, it's 113. If I order it and archive it, it's 75. And again, 76. Again, why is an ordered index faster and more compact? The answer is that like data tends to clump together. My data values for columns today are more similar to tomorrow than they were 10 years ago. So you can see column store compression is amazing. It gives us a lot of space savings and therefore memory savings. This is kind of just a sampling of how it would look if you do it.
I just have to say, when I demoed clustered column stores first time, and I prepared my demos, and I saw this exact thing, that the clustered column store ordered with Columnstore archive compression, it's 1.5% of the original size. And I just thought I must have misunderstood the metadata. So I tried to find, am I missing, is it stored in another metadata table or system table in SQL Server? Because I just couldn't believe that the compression was that good. So.
Yeah, definitely. I've written and spoken on this topic of compression. If you're interested in column store compression, it's a pretty vast, interesting topic of how they make it so small, but this is lossless. This is real. I turned 5 gigs into 76 megs, and it works. And the archive compression is a smidge slower, but it works, and it's fast. Cool. Maintenance. Fragmentation is really only caused by a few things. If you do deletes, you get fragmentation via those soft deleted rows. And if you do updates, you get fragmentation because you soft deleted rows and you've inserted them back on the end. So if I update, let's say I have a data set that goes from 2010 to 2020. I take a row from 2012 and I update it. I delete it, and then I insert it onto the end. So now my 2012 row has been inserted onto the end with the 2020 data, and it's out of order. If you do this over and over and over time, your data becomes out of order. I call that fragmentation. It's not the classic definition of fragmentation, but it's bad. You want well-ordered data. If your data is well-ordered, you actually don't have to do a lot of maintenance to it. You really don't. Unordered inserts, same thing. If I insert data at the end of my index for 2012, 2015, 2005, and I keep doing that, it's going to be all out of order. And then querying is going to require me to get more row groups because I have to get every row group that can have data in it for the values I want. Min-max just checks the min and max in that metadata and checks for it. So an important key to maintenance is that if you have a very well-ordered insert-only column store index, or you only delete off the tail end where the old data is, you won't have to do a lot of maintenance, and it'll still be fast. I really do mean that. Very little maintenance. What can we do? A reorg is online. It will you can, if you want, forcefully process your Delta store contents and get it out of there. Some people do that to make their index as fast as possible after a data load. If they do one data load a day, you can do it. You don't have to. It's cool. A reorg can remove the deleted rows, and it can combine undersized row groups in newer versions of SQL Server. It's pretty amazing. A rebuild completely rebuilds your index from scratch, and so it just eliminates all fragmentation, and it'll try very hard to put everything back to the 2 to the 20th rows per row group. So the reorg will get you most of the way there. It may not get you all the way there. A rebuild will redo it all from scratch. Note that these two operations will not reorder your data. If your data is out of order, it's up to you to slap a clustered row store on there and reorder your data before you go ahead and add your indexes back and rebuild and do all your work with your clustered column store or your non-clustered column store. Your data order is your responsibility, and none of these things will fix it for you. Only you can fix it. Some people do maintenance right after the data loads, as part of the data loads. Some do it once a month, once a quarter, once a year. You can separate it by partition. So if you have partitions that go active to inactive, you can do maintenance separately. You can even be slick and do partition swapping to pull out of the active area, do your stuff to it, and put it back if you really want. You can do these things online, so you don't have to. It's really up to you. But you have a lot of considerations there for partition that are pretty cool. You can do non-clustered column stores. I know we're running down on time, so I'm going to wrap up in the next 5 minutes, I promise. Non-clustered column stores let you basically do real-time analytics on transactional data. So you have a transactional table, clustered index, maybe some non-clustered indexes, row stores. You want to throw OLAP support in there, you can do a non-clustered column store. On the cluster, you can specify your column list. Therefore, if you have a 50 column table, but you only need 2 or 3 columns, just index those columns. The order is defined by your clustered row store. You can't control it. You're stuck with it. That's life. If that order is good, great. If the order ends up being some ID that's irrelevant, then you may not get a lot of gains out of your column store. Sometimes a covering index, a classic covering index, may be okay. Try testing it first, because the maintenance of a column store in a very write-heavy table can be expensive. The ideal target for a non-clustered column store is a transactional table you just happen to not do a lot of updates. That's really the ideal scenario. And you don't insert things out of order very often. If your data is kind of ordered by the columns you want it to be ordered by, and you don't update really very often, then a non-clustered column store can be pretty awesome. But definitely test your reads and writes before doing it. Make sure it really is faster than the alternatives before doing it. This isn't always ideal. It can be, it isn't always. The ideal solution, according to an architect, would be separate your OLAP and OLTP. We can't always do that. I get it. If you can't, this is a slick way to index a few columns and make them fast for analytic queries. We can demo this. So I add a non-clustered column store. I'm pretty sure I've already done it on a table. And this is a table with no order. This is a table that is just a regular old clustered row store. I throw a non-clustered row group, non-clustered column store on there. I run my analytic query. And I note that I read 25 segments and skipped 0. Now, it was fast because the stuff is compressed, but I did do a lot of reads. It was expensive. And I didn't skip any segments because I have no row group elimination. So in this particular case here, the order that I filtered by on my column store analytic query was not the order of my data. And so it I can use the column store, but it probably wasn't worth it here. I could do a covering index instead and insert data. And the covering index is just a classic non-clustered with an include column. And I can run my same query from earlier. And if I do, I get my results. And I will note that I did less reads. Now, it did involve reading a non-clustered row store covering index, but it did do less reads. And it may have been faster. So always test, be sure what you're doing is fastest and best. If not, maybe not the ideal case. Column store is not for everything, and that's life. Somebody asked the question, oh, what memory optimized? Well, memory optimized tables are really meant for transactional data that's very churny, very deadlocky, very blocky, very locky, very, very contentious data. That's really not the data that's meant to be put into a column store index. You can test it. You can try it. I generally advise against it because it often won't give you the benefit you want. It really won't. You can try, but memory optimized tables aren't really meant for this. You can try it for real-time operational analytics. It might work, but I would say it's like 10 to 1, not work. So try it, test it, play with it. If it works, awesome, but don't be disappointed if it doesn't help you. So performance notes that are useful here. There's no free lunch. At the end of the day, you're reading segments. Segments take up space. Every query you read, or every read you do requires reading segments in memory. Reading 100 segments is reading 100 segments. I can't make it much faster. So always keep track of the fact that you're reading segments, and ultimately you're slicing your column store index vertically and horizontally. The more you slice it, the less you read, the faster it is. Ideal performance requires ordered data. Partition if it's big. Use bulk insert whenever you can. Avoid updates. Try to minimize deletes, especially the unordered ones. Ordered ones are okay. Rely on row group elimination, rely on segment elimination, and also make sure you have enough memory. If you have to read, let's say, 100 or 1,000 segments to satisfy queries, whatever it is, make sure you have memory available. If your server lacks memory to support the column store segments getting read into memory, you're going to be always reading them in. It's going to be slow. Make sure you have memory. Memory is important. Compute is important. Don't forget that you have a server with resources out there somewhere and you need to compute. All right. To wrap this up, I appreciate you being patient. I went a little bit over, but it's a 60-minute session. You know how it works. So you really can store your analytic data in SQL Server natively alongside other data, transactional data, whatever. And it's fast. It's very, very fast. It compresses beautifully. query speeds can get much, much faster. And the maintenance isn't foolproof. You can't ignore it. You can't set and forget it. But you really can, if it's ordered, do very little to keep it fast. And it's really nice. You can scale indefinitely. I personally maintain Columnstore indexes with tens of billions of rows, and they are fine. They perform beautifully. You can do that. So if you need that as a use case, feel free to go for it. It's a great tool. I love it. I personally use it a lot, and I recommend it. If you don't want to take your data out of SQL Server right yet, for any reason, this is a great place to park it. This is a good time for questions right now. If you have more after the session is over, feel free to contact me directly. I'd be happy to chat on Twitter or anywhere else. I will post all the session info as soon as we're done. So you have the slides, so you have the SQL, and feel free to ask anything you want to ask.
This was a great way to end the SQL Friday season. Thank you so much. It was a great session.
I didn't go too slow, did I?
You didn't go too
okay, I'm
slow,
just making
no.
sure. I get told that all the time. I'm just kidding. I'm kidding. Cool. Any questions?
One more, except ones we already asked. Well, actually, there were two. One is how can we find the fragmentation, and then Milos posted a script to Nico Neugebauer's GitHub.
Nico is very good. If you see Columnstore stuff from Nico, you can totally trust it. He knows what he's doing. He's a great guy. So use him for info if you want. But yeah, you can check your row groups and your segment metadata for misordered data. Check those min and max values in your segments. If you order your row groups and they order and go up over time, you're in good shape. If they're not, your data is not very well ordered. If you look at your row groups, do they have 2 to the 20th rows or do they have 100? If you have very low row counts, lots of delta store, lots of delete bitmap, you may very well have fragmentation that you want to fix.
Gabrielle wonders if partitioning has any drawbacks or limitations, I guess, when it comes to Columnstore specifically.
They're minor. I would say 2 drawbacks to partitioning. One is complexity. You are adding complexity to your database tier. You're adding partitions, a partition function, a partition scheme, and you have to keep track of those as an architecture administrator. It's not complicated, but it is an additional layer of complexity, and that is a downside in my mind, even though I do love them. I love partitioning. There is a more legitimate Columnstore specific downside, and that is that if your partitions are too small, you will slice off your row groups and have undersized row groups. So make sure your row groups are big enough. Even if they're big enough, you will still slice your boundaries into 2. So wherever your data kind of flips from partition 1 to 2, you will slice your row groups up and have some extra row groups. So you will have more row groups with partitioning. That isn't necessarily bad, but it is a downside. So just make sure your partitions are big enough and you'll be fine. But if they're small, you will suffer a bit and you may not help your performance at all. The maintenance benefits of partitioning, though, are huge, and I highly recommend them. If you have billions of rows, last thing you want to do in production is be like, delete 1 billion rows, go, and then wait a while. Or I got to move 1 billion rows, go, and you wait a while. Way faster to partition truncate, partition swap, snazzy stuff like that seems like magic.
People ask where they can find the scripts for today. Do you have a GitHub where they're stored?
I will link everything on my Twitter right afterwards for you. So you have it, and it's available. So feel free to check my Twitter afterwards, and if you want, you can download them and post them anywhere you want. Feel free to steal my code. I do not mind at all. Give me credit if you're being nice, but feel free to steal as well.
Yeah. So I posted the link to your Twitter account. So just follow Ed and you will see the post. Manish says, in SQL 2017, there was a limitation to not have any timestamp type attributes in tables if we have to introduce Columnstore indexes, and we needed to drop that attribute. Is this now available in SQL 2019? And I guess it's the row version it's called nowadays.
I honestly don't know. I wrote about this yesterday, and I already forgot the answer to that question, so I apologize. I will look up the answer and post it afterwards. I literally was writing about this yesterday, and poof, it clearly went from my head onto the screen, and now it's out of my head, unfortunately. So I do apologize, but I will give you an answer to that afterwards. Our timestamp supported in 2019 and 2022. I will answer that question for you, I promise.
And then Marek wonders, any idea for workaround to something that currently is not possible? A view that would do union between 2 tables, one row store and the other column store, archive version of row store.
Yep, you can do all kinds of workarounds with that. That is a great idea. You can combine Columnstore and non-Columnstore data, and they'll get read the same way. You can do a lot of cool, slick things if you need to. For example, let's say you have data that's very current that gets inserted, updated, deleted a lot. You probably don't want that in your Columnstore, but you could add it in later, and that is an option. That's a very great idea. Thank you. I appreciate that. That's cool.
Yeah, and it's something that I call it the poor man's partitioning, because before SQL Server 2016 SB1, partitioning was an enterprise feature, and most of my clients at least don't use enterprise for some reason. If they have a window to do index maintenance where no users are in the system, they don't use enterprise basically. And then using views, which does union all with tables and so on. It's partitioning. It's how it started, and that's how it's stored in the underneath as well.
In my mind right now, I have flashbacks to like old tables I built years before Columnstore. They had like quarterly partitions that went back for like 20 years, and there were just, I don't even know how many rows in there. And then one day I just said, hey, we can Columnstore it, and it was just magic. And it got simpler. It got so much simpler. It really did.
I worked with a telecom company who had, I mean, they had data ages and ages back of, not, some of the call data was stored for financial purposes, and they had this view with the tables. They were all on separate file groups, and they had lost the disk where some of the file groups were. So the table still worked, but when we were migrating to VMs in Azure and so on, we had to rebuild it, and I set up some kind of log shipping for it, and it was such a hassle because we lost the file groups. So the table was still online, but we couldn't do much with the table because we couldn't drop the file groups because they were not empty. We could not empty the file groups because we didn't have the files. So
has anybody here had a day like that? It's a good time for a drink if you had. Wow.
And it just went on for years and years because they couldn't do much about it. They still needed the way to do it would be to just bulk all the existing data to new tables and so on, but they didn't have that window to do it. Great presentation. I am sure you can speak faster, says Gabrielle.
It's true, I can. Just don't encourage me. I've had no coffee today, by the way, as we already have established. So just watch out.
Yep. So that's why you were so slow, I guess, because you didn't have.
You go. Exactly. I'm gonna probably have my 1 liter of coffee in the morning, my 1 liter of coffee in the afternoon. That keeps me going through the evening when things slow down in my life, because I do the wake up early thing. We were chatting about it earlier before we all started. That I'm up at 4 in the morning. That's normal for me. It's pretty frightening for other people, but normal for me. I like it, but it slows down later. Any other questions, by the way, before we ramble too far off into the world of how we sleep?
No more that I can see. So if I missed the question from the chat, then please post it again, and I'm sorry in that case. But yeah, I think I covered them.
And feel free to ask me later too. You can just email, tweet me. It's no problem at all.
Italian coffee is compressed, is what Gabrielle says.
Love it. I love it. Thank you. Good jokes. Good data jokes. I love it.
Cool. I'm gonna go home to my kids. They started their summer break today. Well, one already had a week. It's starting today. So
I hear my 2 kids above my head right now. I can hear the footsteps going around right now. You can't hear it, but I hear it. So it's great. It's great. They're waking up. They're getting ready to start. They have like 1 more week of school, and then I don't know what I'll do.
How long summer breaks do they have in where you live?
About 2.5 months, I would say. 2.5.
Okay. Same as here. Yeah. It's hard to be, I could of course send them to some kind of daycare center, at least the younger one, but he wouldn't like it that much. But it's hard. They have 10 weeks of vacation and I don't. So I have to figure something out for them to keep occupied with something.
It's hard for you.
And they have all the time in the world. They want to do things. Like I imagine myself at like 10 in the evening saying, wow, I have a half hour free time. What do I do with it? Oh my goodness. Will I play a
Yeah,
game? Will I sleep? Will I eat finally? And the kids are just like, you know, they have all day. I can't even
yeah.
imagine what I would do with all day. Like, what does all day even mean anymore?
I know what I did at like age 11. My mother was so worried because she was like, it's your summer break. You should be out playing football. And I was learning to program on my Commodore 64. She's like, it can't be good for you, all these computers and stuff.
I did that too. In high school, I got my own computer at home and I broke it, fixed it, broke it, fixed it. It was like just a game. My parents were like, what's wrong with it now? And I'm like, hang on, pull the case off, begin mucking with it. And like that was the intro to like my career. And you know, it was like it
Yeah.
started off with, what are you doing? You stink, you're ruining everything, you're wasting money and time. Then it evolved over time into, oh, that's nice what you're doing now. That's a career, isn't it? That's cool. Things changed.
Yeah, I think it wasn't until I even started computer science studies in university and still didn't understand that this is actually a career move. Uh, it was my hobby. I wanted to learn more about programming, and only when I got my first job, I realized that I get more money than my friends who are carpenters. Cool.
Mm. You also find out that your company can make it less fun sometimes. But aside from that, you can still do it and be paid for it, which is kind of cool.
Yeah. So nice. Everyone says great session and thank you. Splendid session. And I agree. It was really perfect way to end the season. And for everyone, don't forget, call for speakers for next season is open, and I do encourage any new speakers to submit the session. You will have a special queue with people who get more easily selected if you're a new speaker.
And I do highly agree. Like, if you haven't spoken before, if you've only spoken in a small venue, like at a company or at a user group, just do it. It's fun. And if you mess up, no one's going to blame you. They're not going to give you a hard time. It's a learning experience. I've done it. I've had horrible things happen in sessions go wrong, and people have chuckled. I made a few little, blips today. It happens all the time. So I highly encourage you to speak. It's a great thing to do. It makes you a better communicator. It makes you better at what you do. Get embarrassed sometimes. Get a caught in video. It's fun. All the good stuff.
My first user group presentation that I did, I had done a few presentations at work, but never for like data professionals. I was a bit nervous, and all my demos were just broken. It was about the ascending key problem, and I had, when you're nervous, you start doing your demos, and I was on the wrong instance, so I had a too new version of SQL Server. So it kind of nothing worked basically, because it from SQL 2014 and later you have the optimizer handles ascending keys differently. And I just couldn't show any of the problems that I wanted to show, and everything broke. But it was an experience as well. I had some MVPs in the rooms who were really helpful, and we talked about it afterwards, and they showed me what I did wrong. They didn't want to interrupt me during the demo and tell me I was doing it all wrong, but it was really nice. And I think the data community, especially what used to be called the SQL community, now data platform community, it's really a helpful one. You will find people who will help you become a great speaker if you want to be a speaker.
And I will say there's few tech communities like this one. Most out there, if you go into other worlds, like the AWS world or the Oracle world, and you're like in those communities, you'll find everyone's trying to cutthroat each other to win. They want to win the bonus, win the award, win the job. Like, this is not this way here. People still want jobs, but like everyone's trying to help each other out. And I found that the many of the people I've met and spoken to and gotten to know better, like, we've helped each other out so much over time. It's a huge deal. So I just, I recommend just talking to people and learning about the community, because there's a lot of helpful people out there. You can just tag like SQL help or SQL family and get interesting stuff on Twitter or LinkedIn that you wouldn't expect. And a lot of good people out there, a lot of helpful people that make our jobs and our lives a little more fun and a little easier.
I mean, even just going to data events like SQL Saturdays and so on will broaden your network. But I found that when I started doing speaking at events, it became more natural, more easy to just approach people. Maybe they heard my name. I definitely heard your name and others, and it's easier. You meet up in the speaker room, and you find friends for life, basically. So it's do it.
True.
I'm gonna leave now, but thank you so much for coming, and I hope we'll meet soon, like be able to actually shake hands and stuff like
I
that.
would love that, but thank you very much for having me. This was fun. I enjoyed the questions. They were great. They really were like perfect, interesting, valuable information. But thanks for having me. And yeah, in person, I really hope in the future we can do it.